Hello, everybody. We are continuing again with the topic interiors of the molecule. In the last sessions, we discussed inductive effect as one of the important phenomena by which you can understand what is happening in the interior of the molecule. And inductive effect is also called as field effect, if you remember. And then we have switched over to mesomeric or resonance phenomena and understood how the electrons pi and lone pair move about and how do you assign their positions if you take a resonance hybrid properly. Apart from these two, now we are considering one more phenomena that is called as hyperconjugation. Let me write that for you. Hyperconjugation. So this constitutes our next phenomena which will help us to have a very clear perspective about the interior of the organic molecule. Now, this term has two parts here. One is conjugation, this one, and you can recognize conjugation by this time because you know the structure, if it is to be called as conjugated, must have a particular structural requirement like a single bond and abetting on both the portions, shoulder portions, we must have some mobile electrons like two pi bonds or a pi bond and a lone pair or a pi bond and a vacant orbital. Therefore, conjugation structure is applicable both for ground state and also for the excited state in which we are considering the reaction. Now, once I say hyperconjugation, hyper means what? More than expected, more than expected. Hyperactive children, for example, they are more than expected active. Now, if I say hyperconjugation, that means what I'm going to discuss, I'm taking up not only conjugated structure but something beyond that, which is becoming part of conjugation now. Therefore, this is something like an unusual conjugation I'm talking here. Maybe a rare conjugation which is applicable for particular types of structures. So let us discover this concept and move about as I'm doing right now. For example, what we'll do is I will take one molecule which will help us to discover what is this hyperconjugation as a matter of fact. All of you may be knowing the structure of benzene. As I was insisting, we must be able to visualize the structures in front of us. It's very important. Benzene is a hexagon and with electron clouds above and below that hexagon. If this is the hexagon plane, planar hexagon, you have electron cloud above, electron cloud below also. That means if any reagent which is short of electrons, it can easily approach benzene ring because benzene is a source of electrons. Therefore, any electrophile can approach benzene ring. And in due course, it leads to what is called as electrophilic substitution. Let me write the first point here. This is my benzene ring. And this electron cloud I was referring to. And this is the electrophile. And in due course, one or two steps or a couple of steps like this, one of the hydrogens of benzene will be substituted by this E plus. Therefore, the product formed is this. E. So what do you call that as? This is electrophilic substituting hydrogen. Therefore, electrophilic substitution. Now, my interest is not to talk about electrophilic substitution now. Benzene molecule, because of its known electron density, is attracting electrophile. Now, what is the most important thing we learn here? If benzene is having electron density, and I'm sure by this time you must be convinced, the structure decides many properties of the molecule. So, can I enhance further the electron density of the benzene ring, enhance further, such that the added electrophile, even though it may be weak in nature, can attack the benzene ring. Therefore, I am trying to take in place of benzene a toluene type of molecule. Toluene type of molecule. Let me write it. I am taking toluene is nothing but methyl benzene. So I am taking here methyl benzene This is my methyl benzene, otherwise called as toluene. Now, as you are aware of from our interaction in the earlier sessions, this is a plus side group. The structure must be therefore allowing a electrophile to attack at a much faster pace compared to what it has happened for pure benzene molecule. And that is confirmed also, no doubt about that. This activates the benzene ring beyond what benzene could have normally allowed electrophile to attack. Now, once we know the influence of the structure on the reactive to a benzene molecule, I am planning like this. Can I further increase the inductive effect of the group? What is the idea here? If the inductive effect is further enhanced, there will be greater electron density inside the ring, and I can expect the reaction of an electrophile with a new molecule with more number of what's called plus side groups. The attack should be more faster. So what I'm going to do is I'm trying to be more ambitious. I want to make this more reactive. So let me write. What I'm doing is I will this benzene molecule. This is my CH3. So what I'm doing now, I want to increase the inductive effect of this. Remember, I'm not dealing with mesomeric, inductive effect only. Therefore, what is the next thing I'm doing here? I'm taking benzene molecule with CH2, CH3. Now, what is the purpose of this? One of the hydrogens here are replaced by CH3, ethyl benzene. Do you realize there is electron density more because of this plus side group? So what is the expectation? They should polarize electrons down into the benzene ring much better than what was happening here. Now, I continue with this ambitious program of increasing electron density inside the ring due to inductive effect. I am writing one more molecule. CH, there is one CH3, there is one more CH3. Do you realize I am having two more groups? That is, it is isopropyl benzene. I am expecting as per inductive effect still greater electron density here. Lastly, even that left out hydrogen will substitute with the methyl group. So I am taking here methyl group. This is methyl, this is one more methyl, this is one more methyl. So electrons are polarized heavily toward this attached component to ring. This is tertiary butyl benzene. First molecule is methyl benzene, ethyl benzene, isopropyl benzene, and lastly tertiary butyl benzene. So by the time I am coming to the fourth molecule, as per the knowledge we have acquired about inductive effect, we expect this molecule can react even with a very, very weak electrophile. Whereas same weak electrophile, if I have to add to benzene, the reaction may not be possible. Now, what is the basis for this prediction here? Only one thing, we have increased the scope of inductive effect here. So this is the expectation, theoretical expectation based on inductive effect. Now, let us do the experiment to verify whether this expectation is confirmed through an experiment. Suppose if I add an electrophile, same electrophile, separately to 4 different containers. Electrophile to this, next container to this, next container, same electrophile to this, fourth container this. And we observe experimentally, the first molecule reacts fastest, not the fourth molecule as we expected from inductive effect. The beauty of science is we must honor experiment, and based on experimental observation, we need to modify our theoretical approach. What is the theoretical approach we have built up to understand reactivity? If it is sigma bond, we say it is through inductive effect, basically electronegativity only. Otherwise, the second factor that we have invoked is mesomeric or resonance effect. And I can't talk about resonance because the group that is attached, any one of the 4 here, they do not have any lone pair in conjugation with the benzene ring. Therefore, resonance we need not consider. We have to consider only inductive effect. And the prediction based on inductive effect is not getting confirmed. We are getting a contrary result. That means, compared to inductive effect, there must be some other pathway by which electrons are coming from substituent into the ring. I repeat, some other pathway apart from inductive effect. Inductive effect is polarization. That we are sure. But now we have to talk in terms of an alternative pathway to understand this observation. Now, how do we identify that? How do you discover that? For example, if you watch out here, the first molecule has good reactivity. Let us imagine this is reacting some arbitrary number 4. Imagine. Now, moment I go for the second molecule, it is reacting with 3. That is, the reactivity has come down. Everything must be accounted in terms of the structure only. Just watch out, please. What is the difference in structure? Not the benzene ring, but the attached group. There are 3 hydrogens in the first molecule, and now one of the hydrogens are replaced here. So only CH2 is there, CH now. CH2, CH3. This is reactivity has still come down, relative number 2. One more hydrogen has decreased here. Lastly, this is 1. That means if you look at the reactivity pattern, I think it has something to do with the number of CH bonds attached to the bonded carbon atom. 3 hydrogens more reactive, 2, 1 and none. As the number of CH bonds are decreasing, I don't think that extra alternative pathway is functioning. Alternative pathway is not there. In that case, by the time we are reaching the last molecule, I think it's only inductive effect that must be considered. So, the CH bond that are there must be part and parcel of our discovery of the alternative path of electron movement into the ring. It does not mean inductive effect is incorrect case because it is unable to account for something new. We are trying to search for an alternative pathway which is functioning simultaneously along with our inductive effect. If that is the case, let us focus on the CH bond attached to the ring. That is the main thing that will be kept in mind. I repeat very quickly, the number of CH bonds influence the reactivity of the benzene ring, or the number of CH bonds here have a role to increase the electron density in the benzene ring. So how many CH bonds are in the last molecule? None. Therefore, it is just an inductive effect that is operating. There is no scope for hyperconjugation. Secondly, larger the number of such CH bonds, I think greater is the reactivity. This is the observation one can derive if you spot out the differences between these structures and correlate with the reactivity. So, I want to write down the first molecule again and focus on the CH portion, nowhere else. Therefore, I rub out the other things. Here and I will rewrite my benzene structure again. Try to follow. This is my benzene structure, KQD structure, and I will be writing one H separately. These 2 hydrogens are combined right down by like that. What is true for this? I think it must be true for remaining 2 hydrogens also. So for the sake of clarity and for the sake of focus, we shall focus on the CH bond. I have written that separately. Now because these electrons must be involved in the ring resonance, and remember this part is conjugated, no ambiguity about that. And this part is not at all part of conjugation. So, if these electrons are getting involved, it doesn't look like a normal conjugation that is sigma electrons, and conjugation normally deals with pi electrons and lone pairs. So, if these electrons are getting involved, this is called as a case of hyperconjugation, more than expected conjugation. So if I am to take these electrons and get them involved here, imagine this is moving here and this is moving here. It may look surprised, and some of you may feel, is it not a desperate attempt? Not likely. Just bear with me for a few more minutes. Then I will write down the typical double-headed arrow mark to indicate what I am dealing with is resonating structures. I am redrawing the structure now, try to follow. No change, and this has become minus charge, this has become CH2 with CH2 plus. That means I have created a clear minus charge in the ring now. Such a thing was not happening in the case of pure inductive effect. A minus charge can be created due to mesomeric effect also. But mesomeric effect means clearly conjugated structures throughout the operation of the resonance. But in this case, there is no such phenomena. It is not throughout conjugated, it is hyperconjugation we are talking about. And remember, the participation of the sigma electrons, the CH electrons with ring resonance, cannot be as fluent as lone pair here, as in the case of phenol. Lone pair is there on oxygen, is it not? I don't think it is on par with this. Therefore, probably the intensity of hyperconjugation may be of lesser magnitude compared to our resonance phenomena. At the same time, it must be stronger than your inductive effect. So, my point is, if I have written this first structure, try to follow. Again, this portion is conjugated, lone pair, single bond, double bond. So, I will rewrite that structure again. My minus charge, if this is coming here, this should move to the corner. So, I am getting a minus charge here, newly formed double bond, and this is CH2 with a plus charge. By this time, you must be acquainted in writing the resonating structures. This lone pair I will move to this corner, and this I will move to this corner. So, what is the new structure again I am getting, please? I am getting a double bond here, a double bond, and a lone pair, double bond CH2 with a plus charge. Again, this portion is conjugated. I wish to write one more structure. So, what is the new structure, please? This is CH3. Now, the following questions will come to the mind of any learner at this stage. If this bond is broken, what is the guarantee that H plus will stay here? I repeat, if this bond is broken, why should H plus stay there faithfully? Correct, well taken question. But remember, your argument is based on a resonating structure. And tell me, what is that you have learned about resonating structures in the earlier classes? They are imaginary structures. They are not existing. If that is the case, your question is based on something which is not existing. Which of them is the real structure of toluene? Is this the real structure of toluene? This one, this one? None of them, none of them. As a matter of fact, we stated this point earlier also. We take one of the molecule as a what's called the representative of the actual molecule. And that molecule could be either this or this because there are no charges anywhere. That is by far the most stable resonating form. Therefore, actually we are not breaking the bond. Then what is the idea? We are showing the polarization of sigma electrons into this. For example, let me tell you, I am rubbing this off here. I want to say, if I am forming a bond, this CH2 and this is a one bond here, two electrons are there. This was the earlier CH3 and remember this is the ring portion for us. Do you remember this is part of benzene structure I am having here? So what will happen? This orbital and this orbital we can expect a bond to form. There is a polarization, that's a bond I am interested to talk about now. You see, every time chemical bond need not be one line with two electrons. There are instances where one line could be equal to three electrons also, or two lines will be equal to three electrons. There are many facets of covalent bond. Not necessarily always one line is equal to two electrons, not that way. So I have written about couple of resonating structures. Now if you carefully follow those resonating structures, I wish to write down now as a hybrid. This is CH2, H, and I think it is continuously moving. This is somewhat a hybrid structure, but this bond is, even now it's not dotted, it is very close to a single bond only, but you cannot roll out this kind of polarization of CH sigma electrons into the ring. This is conjugation, this is not conjugation, though, therefore this is a classic case of hyperconjugation. Hyper, more than expected conjugation is what we are invoking, so that the CH sigma bond electrons shall move into the electrons, by which the electron density in the benzene ring has been enhanced. Now what is true for this CH bond must be true for remaining two CH2 bonds also. Let me write like this, H, H. See, I have discussed only for this hydrogen. I think even this is a CH bond associated with the ring. This is not far away, both. This entire environment is closer to tetrahedral. So even this sigma electrons can be involved. Even the sigma electrons can be involved. Therefore, the collective effort is so many CH sigma bonds are polarized into the ring. If these are decreasing, that much of collective effect is not there. It has become less. It has become still less. And by the time we are reaching tertiary butyl bromide, tertiary butyl benzene, the CH bonds are not there. Therefore, only inductive effect is the only phenomena that is operating here. Whereas in rest of the cases, apart from inductive effect, we also have hyperconjugation operating. Therefore, more the number of CH bonds, I think more will be the hyperconjugation, more will be the electron density inside the ring. Therefore, more will be the rate of reaction of that particular molecule which contains large number of CH bonds. This is an introduction to hyperconjugation. So what we'll do is we'll try to give the applications of this. Before that, we'll try to take some generalizations so that you can recognize in what are the contexts whether hyperconjugation is operational or not. We shall stop now. Hope this is clear for you. We shall take up the next video where we will try to generalize and take the application of hyperconjugation. Thank you very much.